Hey Bhutar Sims, welcome back to another episode of Andrew and I'm on D. Today we're going to be taking a look at why we have the x on the bottom of d over dx. What does with respect to really mean? Okay, so we're going to start off by looking at this plane here. So we've got the y-axis, we've got the x-axis. Now I'm going to draw a random function. Okay, the exact formula doesn't really matter, it's just to show. So we're just going to go, ooh. Okay, there we go. This is a nice little polynomial function we've got here. And the point of drawing this function is to demonstrate what with respect to really means. So if I were to give you the task of finding a slope, let's say I want you to find slope at this point right here. How would you do it? Well, remember the limit definition of a derivative. We have lim h to 0, and what are we going to do? We're going to take another point over here, maybe a bit further, maybe h units, right? This is going to be h units ahead. And so we're going to say, okay, we're going to say f of x plus h minus f of x. So we're going to take the y, the difference in y, which is going to be this distance here, and we're going to divide it by the x distance. So that's just going to be h. This is how we did it. This is pretty simple, the idea. We're only paying attention to a fundamental idea here, which is we're going to be taking this, which is the y, divided by this, which is the x. Right? Remember, slope is y over x. And as h approaches 0 and these 2 points get closer and closer, well, that's the slope of the tangent line. Sick. So, let's get rid of this point. Oh, and I've gotten rid of the whole function. Great, okay. Let's try to do that again. Okay. Shit. Alright, good enough. Okay, here we go. Okay. Here's our point. So, the way we did it is we found a difference in y, right? Oh, let's do that in black. A difference in y divided by a difference in x. And if you remembered, we usually use delta to represent differences or changes. So changes in x over changes of y over changes of x. And eventually we kind of just decided to use d instead, dy over dx, which is the common derivative. That's why we use dy over dx. It's essentially saying a difference in y with respect to a difference in x. We're looking at how y changes when x changes by a little bit. So you may be asking yourself, well, why do we have the with respect to x thing? Because it looks like all the time it's going to be with respect to x, right? What's the point? Why not just use prime notation? Well, let's look at an example here. So this is a graph of maybe what could happen in a chemistry experiment, right? So suppose we've got some reaction going on in a beaker and some gas is being released. So we're losing mass. So maybe our system is going to start up here with the amount of mass. It's going to go down over time, and maybe it's going to cool off. It's just going to end up over here. It's going to keep going. All right. So this is what's happening. Our gas is evaporating. We're losing mass. Well, this isn't really the x-axis anymore, right? This is the t-axis, and this is the m-axis. And we can say m is a function of t. It doesn't. If we wanted to find the derivative of m of t, which actually we would like to find because that would be the rate of our cooling curve. So how would we do it? If we had a function for it, we would just differentiate it. But of course, we couldn't just write it as dy over dx. That doesn't make any sense. What's y? What's x, right? That's why instead of saying y and x in this case, we would say d over dt of m of t. So we're differentiating m of t, which is the function, with respect to t. And this makes sense in this context. We're differentiating this function here with respect to the t-axis, which is the horizontal axis here. It's the same idea. X and t are both horizontal axes. But what we're doing here with d over dt makes it more clear exactly what we're differentiating to. So there is some advantage to using Leibniz notation. So anyway, yeah, that's basically what we're looking at. We're looking at, in this case, how a change in t affects a change in m. Anyway, thanks for watching. Stick around next time where we're gonna be God, I don't know. We'll figure that out. All right, see you later.